Think of Earth not as a solid ball, but as a deep, invisible gravity well, a massive hole in the fabric of space that everything on the surface is trapped in. To leave, we don't just go up, we have to climb out of this well. Now, this is the fundamental paradox of the whole thing. To get out, you need an incredible amount of fuel, but that fuel itself has mass, which means you need more fuel just to lift the fuel you've already added. In this episode, we're going to break down why the up direction is actually a lie, and why the sideways direction is the only way to truly escape the planet's hold. Imagine the launch pad. The ground begins to tremble, a low-frequency vibration that you can feel in your chest. Then, the roar of the engines ignites, a pillar of fire and smoke that obscures everything. The sheer scale of this is terrifying. To get a sense of the force required to leave the planet, just look at the Saturn V. It was the largest and most powerful rocket ever successfully launched. It stood as high as a 36-story building and weighed more than 3,000 tons. When those engines fire, they aren't just pushing a vehicle upward, they are fighting a battle against that massive gravity well. And in a few moments, we'll look at the most dangerous moment of the flight, the point where the atmosphere literally tries to crush the rocket, known as max Q. Our understanding of these giants didn't happen overnight. It started far smaller. The first known rockets were introduced by the Chinese in 1232 AD. These early Chinese rockets were simply fire arrows, long arrows with gunpowder-packed fireworks attached to them. For centuries, the technology stayed relatively basic. By the 16th century, rockets were primarily used for amusement and firework displays across Asia and Europe. Everything changed when the math caught up to the machinery. Isaac Newton's laws of motion provided the first real blueprint for the forces behind rocketry, explaining exactly how to control them. This scientific shift had immediate consequences. By the end of the 18th century, military forces worldwide began applying this understanding to transform those crude fire arrows into powerful weapons of war. It took another leap to reach the stars. The dawn of space rocketry finally arrived in the early 20th century, driven by rapid technological improvements in rocket science and aeronautics. This paved the way for the heavy lifters of the Cold War. The Atlas rocket family launched America's first astronaut into orbit, while the Titan rockets powered the Gemini missions during the intense space race. Then came the peak of this era, the Saturn V, used to launch the Apollo missions to the moon. It was the physical manifestation of a famous resolve. We choose to go to the moon not because it is easy, but because it is hard. To understand how this massive machine actually moves, we have to look at the four major systems that make it work. First, there is the structural system, which provides the frame, the cylindrical body, nose cone, and fins. Then we have the propulsion system, the largest system by space, which houses the rocket engine, the fuel, and the oxidizer. Inside the nose, the payload system carries the actual cargo, whether it is a spacecraft, satellite, or human being. Now, the physics of the liftoff is a brutal struggle against gravity. It all comes down to a force called thrust. Basically, this is the force produced by burning fuel as exhaust gases escape through the engine nozzle. For the rocket to actually move, the engine must generate more thrust than its own weight. This is the critical moment of the power descent. Once that thrust is greater than the weight, the net force allows the liftoff, and the rocket accelerates upward, finally breaking its hold on the ground. As the rocket climbs, something strange happens to its physics. The weight of a rocket changes constantly during flight because fuel is burned off. It is not a static object. It's a bit like a giant, flying, burning candle. As fuel is consumed, the vehicle becomes lighter. This constant change in mass, caused by the burning of the propellants, means the rocket actually accelerates faster and faster as it is pushed upward. This leads us to the most dangerous moment of the flight, max Q. This is the point of maximum dynamic pressure, where the atmosphere literally tries to crush the rocket. The vehicle is moving faster, but the atmosphere is still thick enough to be like a wall of air. This is where the rocket is most likely to break. The structural integrity of the spacecraft is being pushed to its absolute limit, as the air resistance is fighting against the rocket's increasing speed. Now we have to talk about the speed. To truly break free from Earth's gravitational pull, a rocket must reach what physicists call escape velocity. This is the minimum speed required to leave a planet and never come back down. To find this number, scientists use the principle of energy conservation, applying the formula UI plus KI equals UF plus KF. To calculate this, we set the final potential energy and final kinetic energy to 0, representing an object that barely reaches infinity. The starting point is the potential energy of an object of mass m at the planet's surface, calculated as U equals gmm over r, where m is the mass of the planet and r is the radius of the planet. When you run the numbers through the final formula, V escape equals 2gm over r squared, the result is staggering. For Earth, the escape velocity is approximately 11.2 kilometers per second. That is roughly 25,000 miles per hour. To put that in perspective, a commercial jet flies at around 500 miles per hour. The rocket is moving 25 times faster than a passenger plane. If you could travel at that speed on the ground, you could cross the United States from New York to Los Angeles in about 12 minutes. This is where the physics of mass becomes a problem. To get a rocket into space, you can't simply build one giant tank of fuel. If you do, the empty tank itself becomes a massive amount of dead weight that the engines must keep pushing. To solve this, engineers use a technique called staging. In a multi-stage rocket, or a step rocket, a vehicle consists of 2 or main rocket stages, each containing its own engines and propellant. These stages can be arranged in different ways. Tandem or serial stages are mounted on top of another stage, while parallel stages are attached alongside another stage to provide extra boost. Some designs have pushed this further, with rockets that have as many as 5 separate stages having been successfully launched. By jettisoning the empty tanks and engines once they are spent, the rocket follows Newton's first law. Staging allows the thrust of remaining stages to more easily accelerate the rocket to its final velocity and height. You're essentially throwing away the parts of the rocket that are no longer useful, ensuring that the only thing moving toward the vacuum of space is the most essential payload. This creates a transition, because as we'll see in the upcoming explanation of the gravity turn, the rocket doesn't actually fly straight up. It's not just going up, it's going sideways. To stay in space, a rocket cannot simply climb, it must turn. This is where the guidance system maintains balance and steers the flight trajectory as the rocket moves into orbit. Unlike a simple model rocket, which mostly follows the wind or a basic fin's direction, this sophisticated system is constantly calculating micro-adjustments to ensure the craft doesn't drift off course. The goal is to reach a specific horizontal velocity that effectively balances the pull of gravity. The rocket's journey from Earth's surface to orbit is completed when the upper stage engine cuts off at the correct altitude and speed. Once the upper stage engine cuts off, the payload is finally in orbit, moving fast enough sideways that it is essentially falling around the Earth forever. This is the act of achieving orbital velocity, where the curve of the rocket's fall matches the curve of the Earth's surface. When you look at the violence of a launch, the precision is what's actually impressive. This entire flight path is not a lucky guess. It's managed by the guidance system. To keep the rocket from tumbling or drifting off course, the guidance system uses radars and computers to provide stability and control maneuvers during flight. It's a constant micro-adjustment process. The computers are calculating the tilt and the speed in real time, fighting against wind shears and atmospheric drag. We are essentially sending a massive, fuel-filled cylinder of steel and aluminum into the vacuum of space, and the only thing preventing a total catastrophe is a few lines of code and a set of radars. It is the difference between 1,000 tons of scrap metal and a successful mission. The sheer audacity of the calculation is what makes the journey possible. But the current method of escaping the gravity well is brutal. Chemical rockets are essentially giant explosions controlled by a few millimeters of steel. We are limited by the weight of the fuel and the costs of the dead weight problem. This leads to a new frontier, the need for nuclear thermal propulsion or even solar sails. If we can find a way to move without carrying our own massive tanks of fuel, we can truly leave the rest of the solar system. But for now, the only way out is the hard way. Fight the gravity well, throw away the empty tanks, and move fast enough to fall around the planet forever. To escape Earth, we have to fight a battle against a gravity well that wants to keep everything on the surface. We use the 36-story height of the Saturn V to push through the atmosphere, generating a massive amount of thrust to overcome the weight of the surroundings. We push through the same wall of air at max Q, and then we jettison the empty tanks via explosive bolts, triggering the next stage. The goal is not to go up into the vacuum, but to reach a 25,000 mile per hour escape velocity that allows us to leave the planet's pull. Space is not a place you just go up to, but a place you stay in by moving fast enough sideways to constantly fall around the Earth. It's a testament to the scale of human ambition, turning 1,000 tons of scrap metal into a vessel that can leave the world behind.